Let me share my screen to begin. Let me see here. Share screen. And I'm going to share this entire screen here. Reza, can you confirm that you could see my screen?
Yep, I can see that.
Okay, perfect. So yesterday and on Monday, we had the training sessions for PRISMS plasticity, which is up here in the green box. So now we're going to talk about, for PRISMS fatigue, the other modules that we have available. And these are entitled Generate Microstructures.py, as shown here, Calculate FIPS, Volume Average FIPS, Compile and Plot FIPS. The gamma plane, I don't think we will get to, but this is a more complicated script. But the most important things that we need to cover are the first 4 scripts. So these are all Python modules that are available on GitHub. So we'll go through each one and have users understand how to modify these scripts, how they're used, all the files that they generate. And I think these are great files to use, even if you're not interested in fatigue per se, because we first made these to address fatigue, but they can honestly be used to address any types of issues in plasticity. So even if you want to look at, for instance, monotonic loading, not cyclic, that's totally fine. You could still use a lot of these scripts because Generate Microstructures is still going to make you a lot of microstructures that could have texture information from EBSD. And the Calculate FIPS and Volume Average FIPS.py scripts, you can still use those to process information at the local level in your microstructure. So they're still very useful. So with that, what I have opened here, I hope this is easy enough to see. Basically, on the right side of my screen, I have the first module that's open, and that's the Generate Microstructures.py. So that is the up-to-date script that's available on the GitHub page. So that is where you can download or clone the PRISMS-Fatigue. On the bottom left, I have my folder here with the PRISMS-Fatigue scripts. And in the top left, I have a command prompt. And as you likely watched in the introductory videos, there are a couple of software pieces that you need to run PRISMS. The first one being Python, because everything is scripted in the open source Python language. And I think it's written in a way that users can very easily modify different parts of the code. And the other code that you need is Dream3D, and you should already have this from the training session yesterday. The unique thing that I'll mention as well is that Python is installed onto your computer. The way I think about it in like a traditional sense, that you have to install it onto the computer. Whereas for Dream3D, the way I have it, quote unquote, installed is I have my folder here that has my Dream3D 6.5.138 package. But I think you could also, if you have a Linux machine, you can install with the CMake and all that stuff that I'm honestly not too familiar with. This is the way I use Dream3D. I just have the package downloaded on my computer. I see a question. Can I make my slides available for participants? Yes, let me make a note of that. Or Reza, can you make a note of that? And then after the presentation, we can send out some slides, please. But with that, let's continue. So the first script, as shown here, Generate Microstructures.py, this has a lot of functions that you see here that are minimized right now. And the main function that's literally called main is the function that you will edit and change various parameters. So this should be the only place that beginners will make changes to the code. So let's go through some of the settings on top to figure out how to run this Generate Microstructures.py script. But in short, what this script will do is it's going to create, much like in the picture I have shown here, it will create a microstructure or many microstructures in a certain folder. And then with that, it's going to create all the input files that you need automatically for PRISMS-Fatigue. It's also going to create a lot of files that give you a lot of the statistics of the grains and microstructures that you create. So the first variable that you can set is called directory. And this basically dictates where you will create all your microstructures. So there are two ways to define this. You can define it in the absolute path, as I have shown here. So you can just point to a specific spot on your desktop. If you define it in this way, then it will create a new folder called tutorial that's going to be in the same folder as the PRISMS-Fatigue that you cloned from the GitHub page. So that's the first thing you need to specify, is where you would like to store all the files that you make. The next file that you point to is a Dream3D input file. So this has the extension .dream3D, and this contains the statistics of the microstructures that you will make. So right now, the file it's pointing to is called aluminum 7075 random texture equiX grains, and that is also available on the GitHub page. So let's open that up really quickly, and this will be a very brief review of what we saw yesterday. The .dream3D file is basically, all it holds is the statistics of the synthetic microstructures that we will generate. So we have a stats generator filter, and we have some type of grain size distribution here. We have some type of texture. In this case, it is random, and we could have a precipitate phase. So this is a pre-generated statistics file that makes grains that I think are 14 microns in size, as you can see here. So this is what we can point to and say, hey, I want microstructures with these types of statistics. So that is the Dream3D input file. The next thing that we have available is the average grain size. So as you saw in the microstructure, in the Dream3D input file, I just pointed and I showed that that is set to 14 microns. So I specified that here because we need to specify that for some pre-processing code to further manipulate the microstructure. I'm going to talk about two more paths that we need to define. The first one is called Dream3D pipeline path. So this is another pre-generated file called a JSON file. So if we open up this file, this is going to look like what we saw yesterday and the day before that. So this has a lot of other filters in Dream3D, and this is what we actually execute when we call the Python script. You can imagine that if you were to use this in the GUI, you would have to go in and change a lot of settings here by hand if you wanted to make a lot of microstructures. But the beauty in scripting this in Python is that we actually can open this .json file as a text file, and then we can make some modifications by hand. But the Python script does this, automatically. And finally, we point to the Dream3D.exe file, and that is right over here. So this is what we say. This is how we say execute this Dream3D pipeline with this Dream3D input file, and this is where we have the executable file. So this is essentially all the paths that we need to specify where we want to make our microstructures. With that being said, the next basic things that you need to specify about your microstructure are, of course, your size, your shape, and the number of instantiations that you want to make. And these are the next three variables that are shown here. So we have the size is set to 0.0725 cubed, and this is in millimeters. You could make an argument that the size, I mean, it could be meters or microns, but Dream3D has no inherent units. You just need to make sure that you're consistent. But to start, let's just say our size is the default in the script of 0.0725 microns per side. And the shape is the number of elements per side. So this is set to 29 cubed. And we have our number of instantiations set to 5. So with these few settings in the script, let's go ahead and execute generate microstructures.py and see what we get when we run that script. So in my command prompt window here, if you first need to navigate, of course, to the source folder that has all the scripts. And if I type in ls, that lets me know what is in the folder that I am in. And in fact, this has the generate microstructures.py. So now I can run Python generate microstructures.py. And I hit enter, and that will call this script. So we're going to get a couple of printouts here first. The first is that it says current output microstructure file. So this lets us know that it's creating a microstructure. And if we go into the tutorial folder, what it actually did is it made a folder called test run 1, because that is what we named the folder in the directory path. And if we go in that folder, we see that we have some files that start to appear here. So we set the number of instantiations to 5. So we're expecting to have 5 microstructures in this folder when we finish. And once these finish, we're going to go through every one of these files that is automatically generated. I'll specify which ones are generated by Dream3D and which ones are generated by the Python script. And we're going to make sure that we can understand what each file is, what it's used for, and how to further process it. So the script finished. One printout tells us that the total time to generate the microstructures was 63 seconds, so just over 8 minutes. And then we have all these files here in the folder. So let's start with output.txt. This simply stores the output that Dream3D prints to when it creates the microstructure. So you'll see here that it lists the folder or the filter that was run, and it shows you all the printouts that you would expect to see if you were running Dream3D in the GUI, in the graphical user interface. So this is stored here just as reference, so you know what's going on. So like I said, there are many files here. One thing you'll note is that because we specified we want 5 instantiations, 5 microstructures, a lot of these files have a suffix that goes from 0 to 4. So we have, for instance, feature data 0 through 4. We have grain ID 0 through 4, orientations 0 through 4. So each one of these is specific to a certain microstructure. Let's start with visualizing the microstructures that we made. So we can open these to visualize either by double-clicking on the XDMF, which opens up the .dream3d file, or we could actually open up the .btk file. So I'm highlighting these two files here, and we can click on either one to open and view our microstructure. The difference is that with the VTK, I can actually open this as a text file, and you can then manipulate the information of the microstructure here, or read it in Python, or further manipulate it. So I think this is a good output to have. It's not necessary, but you can look at your data and better understand it. But let's open the Dream3D file for microstructure 0 by double-clicking on XDMF. And this is a little bit of a review of what we saw yesterday, but we can open this in pair view. We hit apply in the left-hand side of the screen. On the dropdown, we can go on feature IDs, and then we change our representation to surface or surface with edges. And this shows us our microstructure. So this is the microstructure we made, around 240 grains. If we go on on the information tab, we see that it in fact is 29 elements cubed, because that is the number of cells here. So we can see, we can visualize individual grains, we can visualize the Euler angles, We can visualize the phases. So it's all blue because obviously we only have one phase. One thing that we can specify as well is the boundary cells. So this is something that's made by Dream3, and it basically tells you if a certain voxel is shared between multiple grains. So we can close out of that, and we see that we have these files for the 4 microstructures that we made. Let's look at 2 files that we talked about yesterday and on Monday, and that is called grain ID and orientations. So these 2 files contain the microstructure information. So this is the orientations of the 240 grains of the microstructure. And this specifies what grain each voxel belongs to. So right off the bat, we have the 2 files that are necessary to run PRISMS plasticity, as mentioned by Reza yesterday and on a Monday. So that's great. We're good to go there. Another file that's generated when you run this script is called microstructure parameters. So this is a useful script because it tells you the specific conditions for these microstructures. So say you ran the script a few months ago and you don't remember what you used, what the sizes were. This will tell you that you ran the script in the directory as shown here. The input file that you used is this one here. This is the size and the shape of your microstructures. And then it has some other information that we'll talk about in just a second. The last file I'm going to talk about is the CSV file. So I think this is a brilliant file. Let me drag this on the screen here. So this is a file that lists a lot of detailed information for the microstructure that you just made. The first number in cell A1 is the number of grains, and that is once again 240. And then we have a lot of columns that specify the aspect ratios, the average Euler angles, the centroids, the number of elements in that grain, the number of neighbors for that grain, the volume of that grain, whether or not that grain is a surface feature, meaning that that grain is exposed to the outside of the microstructure, as well as others. The reason that you see volumes multiple times here is because of how certain filters duplicate data in Dream3, but that's not an issue for us, and you can see that this data is repeated. So worst case, it makes this file a little bit bigger, but that's not an issue. The other information we have in this in the CSV file, if we scroll all the way down, we have information for the 240 grains. And then the next chunk of data tells you how many neighbors each feature has and the grain ID of that neighbor. So this means that for the grain with ID 1, that grain has 19 neighbors, and this is the list of those neighbors. So this is really powerful if you want to process this data further or read it into Python to manipulate the microstructures that you made. This is really useful for looking at the statistics of the microstructures that you have just created. If we scroll down a little bit further, so we're expecting to see 240 of these, and in fact we do. The next data set that is generated is the shared surface area list. So we have that we have a certain voxel size. So this next data says that for grain 1, for its 19 neighbors, this is how much surface area it shares between those 19 neighbors. And we have this information for all 240 grains as well. And there's actually, I don't have it here, but you can modify the Dream3D pipeline to also export the misorientation between neighboring grains. So sometimes I see people, you could spend a lot of time trying to calculate that by hand, but just know that if you make a microstructure in Dream3D, it should be very simple to export another section here in the CSV file that actually generates the misorientation between the grains. So this is the CSV file. Let's next look at this JSON file. So we looked at this at the start of the session. We'll look at it one more time, because what happened now is our Python script went in and actually overwrote values into the boxes shown here. So now you'll see, for instance, in the filter that says write Dream 3D data file, it automatically numbered it to 4, because we have 5 instantiations, 0, 1, 2, 3, 4. So you can see how this .json pipeline has now changed, because we overwrote certain sections in a Python. And for quick reference, this export dx file is what generates our grain ID _ text file. Export sc data is what creates our file with our orientations, and export feature data scsv is what exports our grain information that I just talked about just a minute ago. So this has all the information for our microstructures. So let's talk about the philosophy of what we want to do with PRISMS-Fatigue. I hope everyone's watched at least some of the YouTube videos beforehand and read the manuscript associated with this work. But let me go now to another slide of mine, and we'll talk a little bit about what goes on in our simulations. So as I was saying, we are talking about averaging FIPS over grains, bands, or subbands. Really quickly, I'm going to make another set of microstructures that are a little bit more fine to get this point across, because the microstructure I showed is kind of coarse, not a lot of elements per grain, and that's good because you can't always simulate very large microstructures. So I'm going to re-simulate or rerun this Python script. So I'm going to change the directory to create a new folder called test run 2. And all I'm going to do is I'm going to change this to just make one microstructure, one instantiation, and we're going to make it so it has, let's do 60 by 60 by 60. So we just want to refine this microstructure so there are a lot of elements for the sake of demonstration. And I'm just going to check everything else, and I'm going to set these to free. We'll talk about what these mean in just a second, but I want to make sure that I can talk about the band stuff first. So I ran this script again, and as you can tell, I specified a new folder that was created here. And this is that output file that we talked about, and now we have this new microstructure. So there's this VTK file that has the word _bands. So let's open this up here, and this is just like the file I showed previously, but it has extra features for the user. So this is the microstructure we just made, and you can tell it is more refined. There's more elements per grain. And one thing I did here is I appended something else for visualization called bands. So this allows us to visualize bands in the same manner as I have shown on this slide, so that users can better understand how their microstructures are banded for band averaging. So let's see if we could just look at one grain in particular. So I'm going to click on threshold here. For feature IDs, I will specify we want to isolate grain ID number 1. So that is shown here. Let's zoom in on that. And now let's look at the bands. And this is what we have here. So let's also specify surface with edges and rescale the color. So this is a file where you can visualize for you see that we have options 0, 1, 2, and 3 to visualize the bands. And what this corresponds to are the 4 octahedral planes of the FCC crystal system. That's something I didn't mention before, but basically the way we have the code written right now is that users specify what the banding planes should be. So given a grain, depending on the orientation of that grain, the grain will be banded into 4 sets of planes as shown here. And these reflect the FCC octahedral planes. In the generate microstructures.py script, this is specified here at the top. It's called FCC _ oct _ normals. So this specifies what those planes should be for banding. So let's go back on this BTK file very quickly. So, this is good to visualize just so you know, for instance, how many elements belong to the averaging volume for your FIPS or your damage parameters or whatever that may be. So one thing you'll notice here is that we have 0, 1, 2, 3, 4, 5, 6. So we have 7 bands on this grain. So you might be curious about how we specify the thickness of these bands. And then you might also be curious about not only for the bands, but for these sub bands. As you'll read about in the paper, the point of the sub bands is to have a regularized volume over which FIPS are averaged. So these bands here in this more refined grain can obviously vary in terms of number of elements, but the subbands always have the same number of elements. And that's important if you want to compare FIPS that are volume averaged between different microstructures, because you want to hold the averaging volume fixed. So that was a lot of information. Let's go through the rest of generate microstructures.py, and you'll see exactly how users can specify these features for their code. The first thing we specify here is the details of the banding and the subbanding. So for instance, these subbands I show here, there are a lot of, let me see here, quick question. Sorry, do you mind repeating what parameters was changed for test run 2? For test run 2, what I changed was I changed the shape to 60 by 60 by 60, whereas it was set to 29 by 29 by 29. And I only made a single instantiation or a single microstructure, so I changed this variable to 1 from 5. And that was basically just to show the more refined microstructure and how you can visualize the bands. Not a problem. So next thing we'll talk about is how you can specify the band thickness and the number of elements for the subbands. So basically, we're going to talk about, why we have 7 bands for this grain here in particular. Right now, it's set as a percentage of the total volume of the grain. So what this variable here will do is, right now it's set to 0.1. So this will specify that around 10% of the total volume of the grain should be designated to a subband. And the microstructures that we made in test run 1, those have around 100 elements per grain. So by specifying this number to 0.1, that means 10% of the subband volume. That means that the subband will be around 10% of the grain volume. So this will create subbands that have around 10 elements. So then you see that this variable, numvox percentage, is used in numvox. And this is a float, so it's a decimal, whereas numvox is going to be specified as an integer. And I have this right now set that you can specify the code to give you a certain percentage for the subbands. But if you want, you could uncomment this line of code here And this will just say, okay, my number of voxels for the subband should be at 8 or 12 or whatever you think is relevant for your code or for your post-processing. This is where the band thickness will come into play. So you could imagine if band thickness is too small, then you might have bands that don't connect all the way with elements. And if band thickness is too large, then you might have a grain with just two really big bands. Whereas you want to find balance between having, I would say, 5 to 7 bands per grain. You would have to read specific papers that talk about what the damage process zone is in terms of slip bands for your material system. But in terms of discretizing and making a practical microstructures for simulation, the way the code is set up right now is to have around 6 to 7 bands per grain. So that is something you can play with as the user to get a better feel for the code. Right now, I think it's specified to be, around 6 or 7 bands per grain. But once again, you could set band thickness to something else. And this will specify how many elements wide each band should be. Number of planes, basically, I think this will be deprecated and removed at some point in the code, but it basically right now specifies how many bands or how many planes we have. So I said that we have 4 planes for FCC because that is how many slip planes we have. That is how many planes we have to average our FIPS. That is how many planes we have to average our FIPS over. So let's move on. This variable here is called create subbands. So right now it is set to false. And the reason for this is because this can take a lot of time for microstructures that have a lot of elements per grain. And let me explain why that is. So if we have a relatively coarse microstructure like we had in test run 1, let me open one of those again for a visualization. So this is one of the microstructures that has 29 elements cubed, and in total it has around 250 grains. So each grain here has around, each grain has around 100 elements, and it's going to look roughly like this. So when we band it and then we calculate our subbands, the way the code works is for a given band, it will locate. It will start with 1 element and then locate the distance to all the neighboring elements. And then it will designate a subband as the unique set of elements that has the 7 or 8 closest neighbor elements. So you can imagine if there are a lot of elements per the grain, this code will take a long time to run. So what I said here is, if you don't really care about subbands, say you just want to average your FIPS or your damage parameter over grains or bands, you could just set this to false and it's going to save you a lot of time in terms of running the microstructures. To demonstrate that, I'm going to set this to true. And let's go back and I'm going to create a new folder. So this will be called test run 3. And the only thing we're going to change right now is we're still going to make a single instantiation, but we're going to change it back to have 29 by 29 by 29 elements. So once again, we change this to test run 3, 29 by 29 by 29 with 1 instantiation. Make sure you save the updated script, and then we changed, let's make sure we comment this. Hit save again. And we have create subbands now set to true. So I'm going to rerun generate microstructures.py. and it's going to make a third folder here. And once that is done, it is going to create our bands, but then also our sub bands. So you can see that is going on here, and you can tell this is taking a bit of time the way the code is set up. It took around 9 seconds to make the sub band, so almost half of the total time. And the file here called subband info stores all that really complicated information, but that information is also written to these to this .inp file that we can open and visualize as well. This is a large file in size. It's 10 megabytes. So if you're making a lot of microstructures or microstructures that are very big, this can take up a lot of space on your computer. If you don't care to look at these files to see exactly for grain 1, for plane 1, for layer 1, what elements belong to that subband, there is a part of this code where you can just get rid of that and not have it generate that extra file to save space on your computer. But the option is there for you in case you really want to get into the code and figure out what elements go where. The next thing we need to talk about is these two variables here. So one is called face_BC, and one is called compute kosher grain centroid. So to really understand that, we need to think about what we want to simulate. And to do that, I'm going to go back to this slide here. In particular, I'm going to go to this slide, and really quickly, I'm going to just get rid of a bunch of stuff that is going to confuse you. So let me get rid of things we don't really care about right now. So this is a good overview of Dream 3D and Prism's plasticity and review in terms of the types of simulations we can do. So you see here at the top that Dream 3D microstructure generator can make microstructures that are fully non-periodic or fully periodic. So what this means is in Dream 3D, if we make the microstructure periodic, and for reference, I'll show you where that is. So if we open up the .json pipeline, we go to, I believe it is hack primary phases. And this checkbox here specifies whether we want periodic boundaries. So what this means is as we're making our microstructures, as we tessellate our grains, if a grain reaches the boundary of the microstructure, it will start to grow on the other side. So Dream 3D can generate microstructures that are fully periodic as shown in blue or non-periodic at all. And then in terms of prisms, in Prism's plasticity, we have the option to simulate the microstructures as non-periodic using the three boundary conditions as shown here. We can simulate them as fully periodic as shown in the middle, or we could simulate a boundary condition that we call thin film, and that is the last one here. And basically what this does is it keeps two directions as periodic. So in this case, it would be the X and the Z, and the Y is non-periodic. So this would be useful if you're simulating something like a long, thin sheet of material. But the important part is that we need to generate microstructures and then pre and post process them appropriately. And this is where this next line of code comes into play. So face_BC, that is where we specify not just what kind of microstructure we want to generate, but how we intend to simulate our microstructure. So the simplest option is you set everything to free. And basically, if you do that, then this checkbox is not checked. If you set everything to periodic, so if that is the case, then this Python script will go ahead and check that box. But what happens when you want to do this third boundary condition that is called thin film? This is where we talk about this in our latest publication in IMMI. You can email me if you want a copy of that paper. But basically, if we're doing this third type of boundary condition here, we need to generate a periodic microstructure in the X and the Z, but non-periodic in the Y. So that is what goes on in this line of code here. Compute kosher grain centroid. So this is a bit more advanced, but basically what that does is when we band our grains, we need to calculate the center of the grain. So picture you have a periodic microstructure, and it's periodic, so you have some grains that appear on both ends of the microstructure. So when the Python code computes the grain centroid, if half the grain is on this side and half the grain is on that side, it will compute a grain centroid that is right in the middle of the microstructure, and that obviously doesn't make any sense. So what this flag does is it tells the code to compute a grain centroid that makes sense, and that is very important for creating proper bands and subbands. So you can go through the code to better understand that. It's commented very well, and you can let me know if you have any questions through email. But that's important if you want to average anything over bands or subbands, but it doesn't matter if you're interested in just grain averaging. The last thing we need to talk about in this script is this flag called generate new microstructure files. And right now this is set to true. If you set this to false, the entire generate microstructure script will run, but it will not call Dream 3D. So what this is useful for is you can generate a microstructure, and you can create all the files with a certain band thickness and number of elements per subband. And then you can rerun this script and set this to false and create new types of files for banding and subbanding. So let me demonstrate that really quickly. So for instance, we have these files here in test run 3. Well, what we can do is let's make a new folder here. We'll call this folder manipulate test run 3 files. And we're going to go to test run 3. And as I wrote here in the code, we need to copy over the .csv and .grainid.txt. So this file and this file, we copy this, and we'll put this in this new folder that we made. So this has all the information of the microstructure. And when we ran this, you'll remember that we set the shape to 60 by 60 by 60. So what we can do now is beforehand we had a band thickness that was automatically set by this code here, but let's say we want to set that to 1 instead of whatever it may have been. So by copying and pasting this path here, we're basically telling the Python script, re-execute this code to make all the files for banding and subbanding, but do not generate new microstructures by setting, so set this to false. So we're not going to generate new microstructures. We're just going to read the microstructure data that's in here. And let's set create subbands to false. So we will demonstrate how this works to run this script on a microstructure that already exists. And let's copy over the .btk file from test run 3 over to that folder that we just made, because we're going to write the bands to this file as well. And I don't remember what the face BC condition was when we ran test run folder 3, but we can go to that folder and go to microstructure parameters. Okay, so I had the the face boundary conditions set to free. So let me change these to be free, just so we're consistent. And in fact, I had, okay, no, I think that was test run 2 that we had the microstructure. Yeah, in test run 2, my apologies, that was the microstructure that had 60 elements cubed. So we'll actually copy the CSV, grain ID, and VTK files from test run number 2 into this folder here. And just for consistency, we're going to call that 2. And you'll see here that this ended up having a band thickness of 1, or of 2, but in generate microstructures.py, we're setting that to be 1. So everything should be good to go. Size didn't change. The shape is 60 by 60 by 60. The boundary conditions are free. Okay, so now let's rerun this. This has to be set to 2 as well. So now we're going to rerun this script. It's going to read the CSV and grain ID.txt, and now we have another VTK file with bands. So let's open up this new bands.vtk file. So this is the same microstructure we had as before, the one that's more refined. Let's once again do a threshold on the grain number 1. So this is the one we saw earlier, and let's look at the bands. And now we see that in fact we have twice as many bands. So let's do surface with edges, and now for the same grain, what we basically did is we modified the thickness of the bands to be 1 element thickness instead of 2 for the 4 planes. So this shows you how you can run one microstructure, but then manipulate it to create files to average FIPS or parameters over different bands or subbands. So I spent the most amount of time on the script. I think it's the most important one because it tells you how to make microstructures. Like I said, it's very well commented, but in the interest of time, let's move on to the next Python script, and that one is called calculate fips.py. And this is where we're going to work with the data that was available for download. But before we do that, I'd like to ask if there are any questions about anything that I mentioned that I cannot answer. Madan, yes, go ahead and feel free to ask.
Yeah, so you have explained about the bands right now. So what I understand is it is related to slips, right, for the microstructure. So is there any way, how do you assign the slip systems to that, or it is with respect to the grains? So could you explain that?
That's a good question. So the way we have it set up right now is when I define the slip plane normals here at the top of the script, Reza and I made sure that the slip systems as defined in Prism's plasticity align with the way that the slip planes are assigned here. So when you get the, let me show you for instance here. So these are some of the files that you downloaded from Materials Commons that we'll talk about, right? And this has the, this is the grain ID, this is the X, Y, and Z. And this is slip on slip system 1, slip on slip system 2, and so on and so forth. So we made sure that these 3 columns here, slip 1, 2, and 3, that those correspond to the slip plane normal as defined here. So that way, when you run the script and go through with the analysis, you're confident that that the slip that you're averaging from the CSV file, it does correspond physically with the same slip plane as defined in the Python code here.
Okay, thanks.
Not a problem. All right, if there are no other questions, I'll move on to calculate fips.py. So this script is a little simpler. There are only a couple of functions. And to talk about that, this is where we need to look at the data that was on Materials Commons. So I included 3 folders there: free surface effect, grade morphology effect, and texture effect. And this is the data that's associated with our publication of the framework. So if we go into the folder texture effect, this has 4 more folders. The first 3 contain the information for the cubic, random, and rolled crystallographic textured microstructures. I think I have the reference poll figures here. So cubic, random, and rolled. So this is information or data for these 3 textures with the equiaxed microstructure shown here on the left-hand side of the screen. The 4th folder is called simulation files. So this has the files necessary to run the microstructures. So we just talked about how we have the orientations and grain ID files. So these are the other files that specifies what went into the simulations associated with our manuscript. So I'm not going to go over these. What I do want to go over are the files that we then have for processing. So you will notice here we have the grain ID, we have the orientations, we have the BTK files, we have a lot of the same files we just talked about. We also have the CSV files that are the results exported from PRISMS plasticity. So we have these files called maxcomp and max10, and these correspond to the quadrature output from the final points of max compression and max tension in our simulations from our publication. So everything we're going to do essentially reads the information at each quadrature point at those 2 points in our simulation to calculate our FIPS. And there are many types of FIPS that you could define. The FIP that we're going to work with is shown here on the left-hand side of the script. So this is a crystallographic version of the Fatemi-Sosi FIP, and it takes into account the plastic shear strain range on a slip system. So the difference in the value of slip between the point of max tension and max compression, and it takes into account the peak normal stress. It takes into account the peak stress normal to that slip plane at the point of max tension. So these 2 sets of files are shown here. I'm going to open one of these up. I just had it open a second ago, but here it is again. And there are a lot of columns here. Reza yesterday and on Monday specified how you can output certain values that correspond to columns. But as I said, the first 4 are the grain ID, and then the X, Y, and Z position of the quadrature point. And then the next 12 are the values of the current slip at that integration point for the 12 slip systems. So this will go slip 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this will be slip 12. And then what we have is the stress normal to the slip plane. So normal stress 1 for all 12 slip systems. And you'll notice that these values are the same for 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, 11, 12. as expected, because that stress should in fact be the same, because we only have 4 slip planes at each slip system. So let's close out of this, and let's talk about the actual.
A quick reminder that you can find, actually, you don't even have to change the update after increment. We prepared for you the update after increment, calculate plasticity, and all the required file you need to generate the specific format the Python PRISMS-Fatigue code can read from PRISMS plasticity. So if Chris can go and show on the PRISMS-Fatigue GitHub folder maybe later, you can go over all the files on the PRISMS-Fatigue and show the basically update after increment that you can find. So basically you need to copy and paste these 3 files into the crystal plasticity of the PRISMS plasticity and then recompile it. And then after that, if you use one of the input file we prepared or published as a part of publication, then it will generate exactly what you need to process using PRISMS-Fatigue.
Yeah, that's a good point, Reza. Thank you for that. So if you go on the GitHub page for PRISMS-Fatigue in the source folder under material models, these are the 3 .cc files that, as Reza mentioned, you need to place in the correct folder and then recompile PRISMS plasticity. And this file in particular will make sure that you have the same outputs as we have here. Reza, correct me if I'm wrong, but like this is where if they want to add more outputs, like this is what they would modify, for instance, to output the effective plastic strain or whatever other.
That's correct. If whatever new FIPS they want to use, they can just easily modify this quadrature output part, but it should be whatever they define here. This should match the Python code they're using. So that's just the only key point.
Yeah, perfect. So let's go through this code here. This code is a little bit simpler to understand because there aren't a lot of things that you need to change. The first thing that you specify is the directory of the files for which you want to calculate FIPS. And that is the directory file shown here. You need to specify the shape, so how many elements in the X, Y, and Z you have for your microstructures, and the number of instantiations. So if you get this wrong, you're going to get an error. If you specify less num instantiations than you actually have, then you're only going to have it calculated for those, for up to the number that you put there. Here I have specified the type of FIP we want to calculate and the parameters that we need for that FIP. So you'll note in the manuscript for this framework that we have the Fatemi-Sosi FIP, and we specify a value of 10 for K, and sigma Y is 517. Those are the values of K and sigma Y here. So that is where you specify them in the code, and that basically gets passed into this function here. So let's briefly look at this function. All this function does is it goes into the code and it finds these files entitled maxcomp and max10 for the instantiation it's currently working with, and it reads them using the pandas library for Python. So it's written right now to be fairly fast. One thing I'll mention is that I'm not sure if this is relevant, but we use, in this code, we use reduced integration. If you had full integration, then you need to average the values reported in the CSV files here. So then you would uncomment these lines of code. But like I said, everything is well commented here, so you can get a sense of what's of what is going on. And this is where we have our calculations for our FIP. So we calculate our slip values across the final straining cycle. We calculate our normal stress. And then we specified in the main function the type of FIP. Right now it's set to the Fatemi-Sosi FIP as shown here. So here's is the actual line of code where we calculate that for every element in the microstructure. And this is where users can define their own FIPs. So the other ones I have written in here right now are the another type of FIP is the plastic shear strain range. So this is basically the same as the Fatemi-Sosi FIP. It just doesn't include the second part of the calculation that takes into account the normal stress. So that would be just this first part right over here. Another FIP that I have there right now is the normal stress. So what this does is it considers the FIP to be the maximum normal stress at the point of max tension. So this is where you need to think about what you're trying to model in your code. For ductile metals, the Fatemi-Sosi FIP works well, or another type of FIP that takes into account the shear strain on slip systems or plastic strain. But the normal stress, that would be something that is perhaps more applicable as a damage parameter to a more brittle material or metal. But this is where you can add a new line of code. So you would say, elif, if my FIP type is, your custom FIP, then you would perform some type of math here. And then you, of course, have to make sure that the values you need, you actually are exporting using the update after increment.cc file. So the way we have it laid out, I think it's very straightforward to export new files here and then calculate them with the files. But let me get rid of that here. The other thing I have, we're not going to talk about gamma plane. We have a whole YouTube video on that. We're not going to talk about it here in the interest of time. The other option here that we have is this function called append FIPS to VTK. So what this does is we have the VTK files for each of these microstructures, so we can actually append the max element, the max FIP per element to the VTK for a visualization. So we'll go ahead and we'll set that to true for the sake of this demonstration. So let's execute this script. We're already in the right folder. We're still in the source folder, which is where the script is located. Let's do this first for the cubic equiax periodic folder. So I'm going to copy and paste this path here. So we have the directory specified. These microstructures are all 29 by 29 by 29, and there is in fact 30 of these microstructures. We're going to compute the Fatemi-Sosi FIP with these parameters here. There are 12 slip systems, so this is something else you need to specify. But by default, it's more than likely going to be 12 if you're doing a FCC. And VTK visualization is set to true. Gamma plane simulations, we're going to keep that as false, like I said. So let's go ahead and run Python calculate fips.py. And I'm going to, before I run that, we're going to visualize what is in this folder based on the date and time the file was modified, so we can see all the new files. So let's hit run. And you'll notice that we have these new files that start to appear here as .p files. And the code is all done. So now we have these prisms underscore Fatemi-Sosi underscore FIP.p files. So this has the information for the FIPs at every element in our microstructure. And this new VTK file that has underscore appended, this lets us visualize the FIPs on our microstructure. So this has what we had previously. It has the features, right? We can visualize our grains. And we can also now visualize the max element FIP as shown here. So this is really useful because we can see now where are the grains that manifest the highest FIPS in our microstructure. And what's cool is you can go on threshold and you can threshold by the max element FIPS. So we can see where are the elements that cause our FIPS to be highest. So let's go threshold a little bit higher. You know, and we can say, oh, okay, so these are the elements that manifest the highest FIPS. If we change this to feature IDs, then we could see that, okay, this appears to be grain 140. This is grain 160, probably. I don't know exactly, but all I want to get across is that this is a very useful VTK file for finding out where the maximum values are for our FIPS. So let's close out of that. You'll notice that the pickle file with our FIP has the name of our FIP in the file name. So let's say that we want to calculate our FIP as the plastic shear strain range instead of the Fatemi-Sosi FIP. So if we do this, and say we want to do this just for one microstructure for the sake of demonstration, we can rerun this script now. And we're going to have one U file that now has that FIP, plastic shear strain range _0. So now this has a completely different FIP stored in the same type of file in a .p file. And as you'll notice right now, I don't have anything that writes this as a separate .vtk file. So so technically the previous .0 appended VTK file was overwritten, but I guess that's a good note for me to update this. So yeah, we could actually do that on the fly. If I type in %s here, and then I add FIP type. So now that I made this change, okay, so now I have the VTK file that has the max FIP per element for the plastic shear strain range. And if I change this back to Fatemi-Sosi FIP and I rerun this script, I'm also going to have a VTK file for the Fatemi-Sosi FIP. So that was actually a fun thing that I just realized right now that was not in the code. But rest assured, we will push this to the GitHub shortly. Okay, so now we calculated the Fatemi-Sosi FIP for all 30 of the microstructures, and we have those files here. Since we're talking about this script, let's calculate this for the other files that we have here. So we have the random texture equiax and the rolled texture with equiax grade morphology. So while I'm here, I'm going to calculate FIPS for these other microstructures as well. So this is as simple as changing the path of the directory, making sure the number of instantiations is at 30. And we will re-execute calculate FIPS.py. So we're generating the Fatemi-Sosi FIP file for the random texture with equiax grade morphology and the VTK files. So that's all done. And let's do this for the rolled texture with equiax grade morphology. So all we're doing is we're changing the directory. Since the shape is identical and the number of instantiations is 30, we're running that, and that's all done. So now we have we have the FIPS computed for all the 90 microstructures across the 3 folders in texture effects. Let's do the same thing for the microstructures in the folder called grade morphology. And then we're going to plot all these FIPS. But to make sure we have something interesting to plot, I want to make sure the FIPS are calculated for all these microstructures. So let's now repeat that for the 3 folders in the folder entitled Grade Morphology Effect. So we'll start with the one that says cubic elongated periodic. Then we're going to do the same thing to the one that's called random elongated periodic. So once again, calculate FIPS.pi. And then we're going to do it for the rolled elongated and periodic. So I think this will give you a sense of how quickly I can calculate all these FIPS. You know, this, if you ever wanted to do this by hand, this would take you a lot of time and you will make a mistake. The fact that it's automated is so useful. Now we have all our FIPS. The last thing I want to mention about this script is when you make any kind of changes to the update after increments script. So PRISMS-Fatigue, we talked about, this is the file that you will change to output other types of variables to calculate a certain FIP, right? So if you add more stuff here, when you get a new CSV file with a quadrature output as shown here, you are going to get more columns. And you need to know what is in what column. So you need to know that, for instance, these 12 columns contain the slip value. Because in the script here, when we look at slip values, we know that slip 1 through slip 12 is in columns 4 through 15. So you just need to be careful that the way you're reading this CSV file matches up with how the code is written. So that concludes what I wanted to talk about in calculate FIPS.pi. And we'll take a brief break here for just a minute or two, and I can take any kind of questions with regard to this script. If there are no questions, I'll move on to the next one. So the next script is called volume average FIPS. And this is very similar to the previous one. All we need to do is specify our directory where we have our files. We need to specify number of instantiations, and we need to specify the FIP type that we want to average and the averaging type. So do we want to average over subbands or bands or grains? So that is up to you as the user, of course. So since we're in this folder called rolled elongated periodic, let's start with this one. So we're going to copy in the directory for the rolled elongated periodic microstructure. We still have 30 of them. And here we specify the type of FIP that we want to volume average. And you'll note that in this folder, we computed the FIPS that is called the Fatemi-Sosi FIP. So if you wanted to compute, if you want to volume average a FIP that doesn't have the right files in this folder, if you run Python volume average FIPS.py right now, you're going to get a failure because the code is looking for a file called prisms underscore and the name of the FIP. But that doesn't exist, so of course you're going to get an error. So let's change this back to Fatemi-Sosi FIP. And we have the files to average over subbands, bands, or grains. So for sake of simplicity, let's average over the grains first. So we have the correct directory, we have 30 instantiations, we have Fatemi-Sosi FIP, and we're going to average over grains. So let's rerun this script now. And you'll notice that that was really fast. And what the printout here is, it says for instantiation number 0, the largest grain average FIP is this, and that's located at grain 145, indexed at 0. So it tells you right off the bat where your largest FIP is, in which grain. It also produces a series of .p files and CSV files. So let's look at the CSV file first. And this basically gives you the value of the grain averaged FIP. And we saw here that the largest FIP was in grain 145. So if we go to row 145, this should in fact be 0.00387, which is the value that was reported here. So this is really nice because it tells you right off the bat where your highest FIPs are. If we want to average over the bands, we have the files to do that. So all we need to change is change averaging types of bands. We can rerun this script. Now this takes a little bit longer because there are more bands in each microstructure than there are grains. And this tells you that for instantiation 0, the highest FIP is so-and-so in grain 144, but it says indexed at 0, so this is still grain 145. And it tells you the slip system and the layer number at which that highest FIP occurred. So this is really useful because we can track where the highest FIPs are in the microstructure. And we get another CSV file. This one is called band averaged highest FIP per grain. So now we see that the highest band averaged FIP, let me zoom in here, is in grain 145. This is the value of the FIP. This is the slip system out of the possible 12. This is the layer. This is the number of elements in that band. So what's cool here is this is for instantiation number 0. We can actually go and open the VTK file. And we can, let me open the one that has the appended Fatemi-Sosi FIP. So we can open up the VTK file. We can look at all the grains. We can look at the grain 145 that we know has the highest FIP in this microstructure. And we could try to really quickly find some characteristics of this grain. Obviously, this is the grain with elongated grain morphology, and we could see where the elements are that cause the max FIP in that microstructure. I don't have the bands here, but maybe that would be a good exercise for your users, right? So if you took this VTK file, this grain ID file, and this features file, if you copy these into a new folder and you executed generate microstructures.py with that with this set to false, then you can create that VTK file that shows you the bands as well. And then that would show you exactly which band manifests that highest FIP. So let's close out of that. Finally, we have FIP averaging over subbands. So this will take the longest because we have more subbands than we have bands. So if we run this now, we see it's taking quite a bit of time. And we're getting files here that start to pop up. So now we have a file that's called subband averaged highest per grain Fatemi-Sosi FIP. So now we see that the highest FIP is in grain 28, not 145, but 145 has the second highest FIP grain. And obviously, if we look at the value of this FIP here, the subband average FIPs are highest because we're averaging them over the smallest volume. Grain average FIPs are going to be more smeared because you're averaging over a larger volume. And the benefit of these subbands is that the averaging volume is the same. So now that we talked about that, let's go ahead and for the same 6 folders, let's compute the subband volume averaged FIP. So we just did this for the rolled elongated periodic microstructure. Let's repeat this for the random elongated periodic. And then we're going to repeat this for the cubic elongated periodic. Let's see here. Okay, let's run this again. So now it's going to compute that for the cubic periodic microstructure. And these are the three that are in the folder entitled Grade Morphology Effects. And we're going to go to the texture effect, copy in the path here. All we're changing is the directory because we still have 30 microstructures. We want to volume average the Fatemi-Sosi FIP, and we want to average this over the subbands. And after we average these FIPs, then we'll move on to the final script that's called compile and plot FIPs. And we're going to fit these FIPs to an extreme value distribution to visualize how the driving forces for fatigue crack formation across different textures and grade morphologies is different. So that's for the random equiaxed periodic. So the final one is for rolled equiaxed periodic. So now I have the directory there. And once I have this run one last time, I'll take a pause so people that are following along can run through these commands as well. So while this is taking place, the individual functions here, as the name suggests, this is where the code iterates through all the elements that belong in a certain grain or band or subband. There's also a function here called read FIPS from single SVE. This isn't used anywhere, but it's a function that I used a lot for the papers associated with this work. So more advanced users should check out that function, and maybe it'll be really useful for them, but that's for SVEs that are very, very large in size. If you have any questions about that, feel free to shoot me an email. But in summary, that's a extra function for users to use. So now that we have our FIPS volume averaged, I'd like to stop and see if anyone has any questions before I move on to the script entitled compile and plot FIPS. If not, then let's go move on. Let's see here. The way the final script works is that at the top, this is a way to specify where the folders are that we just volume averaged our elements in. So dir loc is this directory here. Let me see here. Dir loc is this folder here. So I need to move something around really quickly. I need to put these files in these folders in the right place. So I need to copy over these texture effects files into here. Okay, that's not taking as much time as I thought it would. And I'm going to do the same thing for the grain morphology. The reason I'm doing this is because the way I set up the script, is to really quickly point to where the files are for volume averaging. So the way I have it defined here is that the code is going to look for these folders in these locations here. So let's go to the main function of compile and plot FIPS. And as the name suggests, this script basically reads in all the microstructure files that we just made to make some type of useful plots. And what we're going to right now plot is we're going to compare the effects of different grain morphology, different shapes. So we're going to look at equiaxed and elongated grains, and we're going to look at the 3 textures that we have the data for, and that includes the cubic, random, and rolled crystallographic textures of FCC. We're going to leave this first setting as is, and that is FIP extreme value distribution. The directory that specifies where we want to store our plots and files that we make. We're going to leave this as is as well. Prisms compare shapes, so that's going to compare the different shapes that we simulated of grains. And we're going to want to average or use the Fatemi-Socia FIPS, and the averaging type we're interested in is subband. So if we average FIPS over grains or bands, then we can use that setting there. But right now, if we change that to something other than subband, then we would get an error. So if everything is done right, you don't really need to change anything in the script except to run it at this point. This will say if analysis type is FIP extreme value distribution, then we're going to specify that we want to plot the 50 highest FIPS from each of those 6 folders. So each folder had 30 microstructures. Each microstructure has 250 grains. So out of that total 7,500 grains from a folder, we're interested in the highest driving forces for fatigue crack formation. So we want to plot the 50 highest FIPS as specified here. The plot type right now is set to Gumbel, but the other option is Frichet. So that is another type of extreme value distribution. And then this is going to call the plot FIPS function up here. And this FIP is the one that specifies properties of our plots in terms of like colors, the shapes of the markers, in terms of the figure legend. It's going to call another function up here that says read pickled FIPS. So let's first, I'm hoping everything works out well. Let's just run Python compile and plot FIPS. And if everything is correct, we should get a nice plot. Okay, so I'm getting an error. Cannot find the path specified. Texture effects. Okay, so the issue was that the cubic equiaxed, random equiaxed, and rolled equiaxed, these actually need to be in a folder called texture effects. So let's move cubic equiaxed, random equiaxed, and rolled equiaxed into texture effects. And if I run this again, I'm going to get another error because I need to have another folder called grain morphology effects. So this is basically the name of the folder that originally had these other folders. So when I copied them over into the tutorial folder, I forgot to structure them in that way. So let's get rid of this. So now everything should work well. Cubic elongated periodic. I think I put things in the wrong folder. Elongated needs to go into grain morphology effects. Okay, so to summarize, in the folder called tutorial, we need the texture effects with the 3 folders, and we need the grain morphology effect with the 3 folders. So if we run this now, we got a lot of printouts. Basically, it printed out the .p file from which it read the FIPS. It indicated to us how many FIPS are plotted, and then it indicated the some stats of the line of best fit. And then we have new files that were generated here. So these .p files, after we read FIPS from a microstructure, instead of having to read those from scratch, the code saves them as new .p files. So if I change nothing and run this code again, you'll notice that all we get now is the printout of the best fit lines. In our case, reading the FIPS from these files did not take a long time, but if your microstructures have a lot of grains, then that can take a very long time. So by storing the highest 50 FIPS in this manner, we basically have faster access to those FIPS. And this is the plot that we just made. And you'll notice that this is the same plot from our manuscript. So what this is showing us is it's showing us the highest 50 FIPS from the microstructures with different textures based on color, and then the different shapes based on whether the marker is solid or hollow. The x-axis is the magnitude of the FIP, and the y-axis is the probability. These units are kind of strange. Really quickly, I'm going to show a better way of interpreting that data. So please ignore this stuff. So if you look in the top right, this is how you read that kind of plot. So basically, based on the y value, that tells you the percentile of the FIP that you're looking at. And the reason we plot FIPS into this linearized version of the Gumbel extreme value distribution is so that data that is truly from an extreme value distribution appears as a straight line. So once again, this is the plot that we just made after we post-processed our FIPS. And this extra CSV file, this basically gives you the R-squared value, the y-intercept, the slope, and then the value of the maximum FIP. So that is just an extra thing that is written into a CSV file. We didn't go through how to compare the effects of a free surface, but if you go and watch the tutorial videos, the steps are very similar. And that concludes compile and plot FIPS. A lot of this code is commented, so if you have, if you want to do a deep dive of the code, I would go and read all the comments. Before I open it up for questions, I want to mention that these scripts here generate microstructures, calculate FIPS, volume, average FIPS, and compile and plot FIPS. These are the original five that we made for this manuscript. Since then, we have a variety of other codes here, and I have these under applications. So if you go on the GitHub page for Fatigue, if you go under applications, excuse me, there are a series of folders here. So these are extra scripts that I wrote over the past half year that I found interesting or useful, or that are associated with new papers. So for instance, this folder called Generate Simple Microstructure, this allows you to generate a simple microstructure. So a microstructure with cubic grains using a Python script and Dream3D. Because right now, Dream3D does not have the option to generate a microstructure that looks like this. So each color here indicates a unique grain with a unique grain orientation. So for instance, if you use this script, you can generate a microstructure that is simple with however many grains you want in the X, Y, and Z. and with however many elements you want per grain. The other folder I'll mention is effects of boundary conditions. So this has other Python scripts to post-process the results of other papers that we've published. So for instance, one of our latest papers looked at the effects of different types of boundary conditions. So this paper was published in IMMI, and we did a lot of cool stuff here. We basically looked at how, for instance, how different types of non-periodic boundary conditions, how those affect the driving forces for fatigue crack formation and the micro and macro scale response. So what we have on this page here is the Python script that we use to make all the figures. And we have a link to Materials Commons that gives you all the data associated with this paper and with those Python scripts. So definitely this applications folder is the place to check out for new and exciting Python scripts or new types of microstructures. But with that said, that concludes the session, pretty much everything that I wanted to talk about. So I'd like to open it up now to Q&A. I hope that was informative. Please let me know what questions you may have, or whether or not you're unsure if PRISMS-Fatigue or PRISMS in general can handle the kinds of problems that you would like to address in your research. So thank you again. And yeah, I'm hoping we could have some kind of discussion at this point.